Okay, so in today's lecture, we are going to finish our discussion of NMR spectroscopy by focusing on C13 NMR. We'll talk about how it differs from proton NMR and what it is most useful for in terms of determining structures. Then we'll start chapter 15, our final chapter on radicals. We will introduce radicals, talk about characteristics of radicals, and then we'll start talking about radical reactions. The first one we'll cover is the halogenation reaction. So in C13 NMR spectroscopy, what we are detecting is the spin flipping of the C13 nucleus. The C13 nucleus, like the proton, has two different spin states, the plus 1/2 and the minus 1/2 spin state. So when that nucleus undergoes spin flipping and then releases energy as it relaxes back down to the lower energy spin state, that energy can be detected in the same way that we detect the spin flipping and relaxation of the proton in proton NMR. There's a big difference, however, between the two techniques. And that comes from the fact that the C13 nucleus is only 1.1% abundant in nature. Most of the carbon atoms we find in nature are carbon 12. Carbon 12 does not have two spin states, and so carbon 12 is not detected using proton NMR spectroscopy, or using C13 NMR. Let me back up a minute. Carbon 12 cannot be detected using NMR spectroscopy. So in proton NMR, we are detecting the most abundant isotope of hydrogen, whereas in C13 NMR spectroscopy, we are detecting an isotope that is not very abundant at all. So the signals are not as strong, and in order to record the spectrum, we have to do several scans of our sample, and we have to use a mathematical technique known as Fourier transform to add those scans together in order to get a spectrum that we can see. So we have here on the screen an example of a C13 spectrum. This is the spectrum of acetic acid, a simple compound. First, let's discuss some of the differences between C13 NMR and proton NMR. The first thing we notice when we look at that spectrum is that it has a wider chemical shift range. The range goes from about 220 ppm at the upfield end. This one cuts off at 200, but you can go up to about 220. And then zero, the 0 point is the same as it is in proton NMR. The reference compound for the 0 point on the scale is tetramethylsilane, the same reference compound we use in proton NMR. So the carbon in tetramethylsilane will show up at 0 ppm in the C13 spectrum. Okay, so we see wider chemical shift range. It's not on our list, but you do see the baseline of the spectrum is noisier. That's due to the fact that it's much less sensitive, that we're only detecting about 1% of the carbons in our sample, as opposed to detecting 99% of the protons in our samples when we do proton NMR spectroscopy. So, second thing we notice is no splitting. In most C13 spectra, the peaks are all singlets. And this should make sense because for a carbon nucleus to be split by a neighboring carbon, both of those carbons would have to be C13 atoms. And the probability of having adjacent C13 atoms in a molecule is about 0.01%. So you're not going to have a C13 nucleus split by an adjacent C13 nucleus, okay? Now, protons that are attached to C13 atoms can split those C13 atoms. So you might wonder, well, why does this CH3, this methyl carbon in this spectrum, not show up as a quartet? Why is it not split by the protons that are attached to that carbon? The answer is that there are special techniques when you are conducting the C13 spectrum. When you're acquiring that spectrum, there are special techniques that are used to eliminate the coupling between the carbon and the protons attached to it. So you might ask, why would you want to eliminate that? Why wouldn't you want to see the splitting to know how many hydrogens are attached to the carbon? Well, the problem is, since C13 is not very sensitive, if the peaks were not singlets, they would be much shorter and they would be swallowed up in this noisy baseline and you just wouldn't be able to see them. So in order to be able to see the peaks, because it's a less sensitive technique, we usually conduct C13 NMR spectroscopy under special conditions in which the splitting between C13 nuclei and the protons attached to them is eliminated. It is possible to run it with the coupling information in there, and occasionally on standardized exams, such as the final exam, you might get C13 data that has splitting information. If you do, you would just treat it similarly to the splitting information from a proton NMR. Namely, if you saw a quartet in a C13 spectrum, you'd know that was a CH3 carbon. If you saw a triplet, that would be a CH2 carbon, and so forth. So usually we don't see that, but if you see it on a standardized exam, it's easy to work with. Okay? And then the third point, I'll write it over here so you can see it over the podium. The third point where it differs from proton NMR is that there's no integration. So the intensities of the peaks in C13 NMR spectroscopy are not related to the number of carbons represented by those peaks. The reason for that is something that you would learn if you take Chem 455. The short version of the explanation is that the C13 nucleus takes a longer time to relax back to equilibrium after you pulse it with the radio frequency radiation. You hit your molecule with a pulse. The C13 nuclei all flip their spins to the higher energy state. The time it takes for them to relax back from the higher energy state to the equilibrium between higher and lower energy states varies widely depending on the type of carbon that you have. And so that variance in what we call relaxation time leads to variances in the peak intensities and means that integration is not useful. Okay, so we're not going to have integration data for C13 NMR, but that's fine. We have it for proton NMR, so we don't really need it for C13 NMR. Okay, so we have a table that shows us common chemical shift values in the C13 spectra. These carbons show up in the regions that you would expect based on the arguments we made with proton NMR. If we have an electronegative heteroatom, that carbon will be deshielded. If we have pi electrons from alkenes or benzene rings, we have strong deshielding. Carbons of alkynes are more shielded than carbons of alkenes or benzene rings. And then a carbonyl carbon is going to be our most deshielded because it is deshielded by the pi electrons as well as by the electronegative oxygen. So all of this should make sense based on what we learned with proton NMR. And so we see another sample spectrum, one propanol, and these three peaks can be easily assigned based on increasing distance from the electronegative oxygen. So that's pretty straightforward. Here we have another one, methyl acetate with a carbonyl group. So, but in my opinion, what is most useful about C13 NMR is that it very rapidly tells us the number of different types of carbon atoms that are present in our molecule. This chemical shift information can be easily obtained from proton NMR for the protons, and in many cases you could figure out the structures of the compounds without looking at the C13 spectrum. So for me, it's most important to look at C13 and to focus on the information that we can gain from a C13 spectrum more easily than we could gain it from a proton NMR spectrum. And that's where it's going to be useful in helping us solve spectroscopy problems. So all we have to do is count the number of signals in our C13 spectrum, and that tells us how many different types of carbons are present in the molecule. If the number of different types of carbons is less than the total number of carbons, which you can usually figure out from your mass spectrometry data, then that tells you that there is symmetry present somewhere in your molecule, that you have some equivalent carbons that are causing you to have less different types of carbons than you do total numbers of carbons. And so when you're choosing between possible structures that have different symmetry elements present, simply counting the number of peaks in the C13 NMR can help you distinguish between those structures. And I'll give you an example. So let's say that you knew your sample compound was a benzene ring with 2 methyl groups attached, but you didn't know at which carbon those methyl groups were attached, okay? So there's going to be 3 different possibilities. You could have the methyl groups adjacent to each other. You could have the methyl groups in a 1-3 relationship. And you could have the methyl groups in a 1-4 relationship, or opposite each other on the ring. So we look at our first example with the 1-2 relationship between those methyl groups. We've got a plane of symmetry that cuts diagonally the way I drew this on the board. And so we have 1, 2, 3, 4 different types of carbons. So this molecule would give us 4 signals in the C13 spectrum. This molecule here, I drew it so that it has a plane of symmetry going vertical. And we see 1, 2, 3, 4, 5 different types of carbons. We've got the 3 that reflect each other in the plane. We've got 2 carbons that are in the plane that aren't reflecting each other. So this substitution pattern would give 5 signals in the C13 NMR. The 1-4 relationship between the methyl groups actually has 2 planes of symmetry. Okay? With these 2 planes of symmetry, our methyl groups are equivalent, that's 1. The carbons bearing the methyl groups are equivalent, that's 2. And each of these other 4, the CH carbons in the benzene ring, are equivalent. That's only 3, okay? So we would just see 3 signals. So C13 spectroscopy would be the quickest way and the easiest way to distinguish between these 3 constitutional isomers. All you have to do is count. If you can count to 5, you could determine which of the 3 isomers you had, okay? So determining the number of different types of carbons and comparing that to the number of carbons in your molecule and determining whether or not there's symmetry present, that's really the most valuable way of using C13 NMR, in my opinion. So we have an iClicker question for practice. So go ahead and pause the video and try to determine which of the methods below would be the most useful in determining between these compounds. And after you've figured it out, restart the video and we'll discuss the answer. Okay, so we can rule out mass spectrometry because these are constitutional isomers and have the same molecular weight and molecular formula. We can rule out IR spectroscopy because these two molecules have the same functional groups and would give the same types of peaks. So we're left with proton NMR and C13 NMR, okay? So when we give this is one of the most challenging iClicker questions we give in class. So in a sense, you're lucky that we're doing this after the class is over, and this is not for credit, or after the in-person part is over. So many students, when they look at this, they say proton NMR, because you'll have a very small J value between these two hydrogens, and you'll have a medium-sized J value between these two hydrogens, okay? That is incorrect. The reason that is incorrect is these hydrogens are equivalent, and equivalent hydrogens do not split each other. These hydrogens are equivalent. There's a plane of symmetry here. Equivalent hydrogens do not split each other. So there's no coupling between these two alkene hydrogens, no coupling between these two alkene hydrogens. So J values cannot be used as a way of distinguishing between these two compounds. However, there is a way to use proton NMR to distinguish between these two compounds, okay? And the one on the left, the alkene hydrogens in the methyl group are too far apart to couple each other. So you'll have two singlets in this structure. However, over here, the methyl group and the alkene hydrogen will split each other. So the methyl group will appear as a doublet, and the alkene hydrogen will appear as a quartet. So you can use proton NMR to distinguish between these two molecules, but it's important to note that the alkene hydrogens will not couple to each other. In the structure on the right, you will have coupling between the alkene hydrogen and the methyl group. So proton NMR will work. In my opinion, the easiest way to tell the difference between these two compounds is the C13. And the structure on the, we'll start with the structure on the right. The structure on the right has two different types of carbons. So we have two peaks in the C13 NMR spectrum. The compound on the right, plane of symmetry goes horizontal instead of vertical. So we have three different types of carbons. So there will be three signals in the C13 of the compound on the left, two signals in the C13 of the compound on the right. So I think C13 is the easiest way to distinguish between these two. Proton NMR also works if you're looking for the right thing. And so this is one of our only iClicker questions that actually has two correct answers. All right. And with that, we conclude our discussion of NMR spectroscopy. And we turn the page to start discussing radicals. Okay? So let's go ahead and raise the board up. So radicals are reactive intermediates that we introduced back in chapter 6. A radical is a species that contains a single unpaired electron. It's formed via a homolytic cleavage or a homolysis of a sigma bond. And radicals have many similarities to carbocations. So as we discuss radicals, we're going to focus on those similarities that they have with carbocations, and then we're going to mention a few differences. One other thing to remember about radicals is that when we draw a mechanism involving radical intermediates, we have to use the barbed fish hooks or the single-headed arrows instead of the full, or the half-headed arrows, I should say, instead of the full-headed arrows, in order to show the movement of a single electron as opposed to the movement of a pair of electrons. So, similarities to carbocations. The first similarity is going to be that they are reactive and not isolated in most cases. There are a handful of stable radicals that can be isolated, but most radicals are reactive intermediates. We're going to form them in one step of a reaction, and then we're going to consume them in the next step, much in the same way that we did with carbocations. Second point, the way we classify radicals and carbocations is the same. It's based on the number of alkyl groups that are attached. So this is a primary radical. This is a secondary radical. And this is a tertiary radical. So that's the same classification system that we had for carbocations. The third area in which carbocations and radicals are similar is their structure. The unpaired electron does not count as a group, so we have three groups on a carbon that bears an unpaired electron. So the geometry is trigonal planar. The hybridization is sp2. And we have a p orbital, and that p orbital is unfilled. Okay. Now it's half filled. In a carbocation, the p orbital is empty. In a radical, the p orbital is half filled. But if we're looking at similarities between carbocations and radicals, we could say that both of them have an unfilled p orbital. Okay. So that's a similarity. Trigonal planar, sp2 hybridized. Okay. And then our fourth similarity, we'll write it over here, is the relative stability of carbocations, or of radicals and carbocations. So our more substituted radicals are going to be more stable in the same way that our more substituted carbocations are more stable. Okay. Alkyl groups can donate electrons. A carbon-bearing radical is electron deficient because of that unfilled orbital. It doesn't have a positive charge, but it does have an unfilled orbital. And so you can donate electrons to that unfilled orbital if you have electron-donating alkyl groups. And this figure here shows that. This is a figure from another textbook. And what we're seeing here is not charge. When we have our electrostatic potential maps, we use red for high electron density, blue for low electron density. What we're seeing here is known as spin density. Spin density is the term that we use to describe radical character, where that unpaired electron is located. And in the methyl radical, we have no way of delocalizing that unpaired electron. It's going to be located on the carbon. But in the ethyl radical, we can delocalize that unpaired electron through induction and hyperconjugation, just like we can delocalize a positive charge. And so you see the spin density can be shared by other atoms in the alkyl group. Okay, so increasing substitution of a radical will stabilize that radical in the same way that increasing substitution will stabilize a carbocation. We can actually use bond dissociation energies as a measure of the stability of radicals. I'll show you what we mean by this. If we have propane, we can measure the amount of energy it takes to cleave one of the primary carbon-hydrogen bonds in propane. That will give us a primary radical and a hydrogen atom. Okay. So the difference in energy between the products and the reactants in this step is 98 kilocalories per mole. So we say the bond dissociation energy of this primary carbon-hydrogen bond is 98 kcals per mole. But in propane, we also have secondary carbon-hydrogen bonds, and we can measure the bond dissociation energy of the secondary carbon-hydrogen bond. And we find that that's lower. It's 95 kcals per mole. Okay. We have the same starting material. We have propane as our starting material in both of these reactions. The hydrogen atom, that's the same. So the only difference in these reactions is the alkyl radical. We get a primary alkyl radical in the first reaction, a secondary alkyl radical in the second reaction. So this difference in delta H is reflecting the difference in stability between these two radicals. The secondary radical is more stable than the primary radical by 3 kilocalories per mole. And that is due to the electron donating ability of two alkyl groups in this case versus just one alkyl group in this case. Okay? So we know from measuring bond dissociation energies that more substituted radicals are indeed more stable. Okay? There is a key difference between radicals and carbocations, and you'll probably be happy about this. No rearrangements. Whenever we have a carbocation intermediate, we're always looking for the possibility of a rearrangement, an alkyl shift or a hydride shift from one of the adjacent carbons. That does not happen with radicals. Now, if you go on to study organic chemistry at a higher level than this class, you might find that there actually are some rearrangements of radicals, but they're not the same as the carbocation type rearrangements, okay? And they're not as common. So for purposes of this class, we will not be encountering any radical rearrangements, so it's not something you'll have to worry about. And I'm sure you're not too disappointed about that. Okay, let's talk about some general features of radical reactions, okay? The first one is that heat or light we use a triangle. That's the Greek capital delta. And then light is H nu. This is the Greek letter nu. It sort of looks like a V, but it's not. So heat or light is used to form radicals. The heat or the light is going to provide the energy to perform the homolytic cleavage reaction that is necessary for generating radicals. Sometimes in our starting materials, our bonds are too strong, and we're not able to directly cleave one of those bonds by using heat or light. In that case, we can use something called a radical initiator. So a radical initiator is a molecule that has a weak sigma bond that can be cleaved using heat or light. And then the radicals that result can be used to react with your desired starting material to generate new radicals. In 2 lectures from now, we'll go over an example of a reaction involving a radical initiator. There are several types of radical initiators. The one that we're going to talk about in this chapter is the peroxide, or peroxides in general. Peroxides are molecules that have an oxygen-oxygen bond. We encountered them in chapter 12. They are oxidants. And if you apply heat or light to a peroxide, you're going to have a homolytic cleavage of that weak oxygen-oxygen bond. We told you that any molecule with an oxygen-oxygen bond, that bond is very weak, and that bond will almost always be cleaved in reactions involving that species. And so we can generate oxygen-centered radicals by homolytically cleaving the oxygen-oxygen bond of a peroxide using either heat or light. And then that oxygen-centered radical, there's technically going to be two of these if we balance the equation. Usually we don't balance equations when we're doing radical reactions. But then these oxygen-centered radicals can then go on and do other chemistry. They can react with starting materials and generate radicals, the desired radicals from those starting materials. Okay? So these are a couple general features of radical reactions. A couple of general processes that radicals will undergo. So we'll keep listing this under general features. Radicals will react with alkanes and abstract a hydrogen atom from that alkane, generating a new radical. So that's referred to as hydrogen atom abstraction. And we'll talk about that in more detail in our next lecture. But the way we would draw that, let's say we had a halogen atom, and the halogen atom collided with an alkane. This is how we would draw the curved arrows, the single-headed arrows, to show that hydrogen atom, or that halogen atom abstracting a hydrogen, breaking a carbon-hydrogen sigma bond. And so what that's going to do is give us an alkyl radical, a radical on carbon, and then we would form HX in the process. Okay? So this is known as hydrogen atom abstraction, a very common process that radicals undergo. Another common process that we have with radicals is addition to carbon-carbon pi bonds. Okay? So here's our alkene. We'll use a halogen radical again. So by adding to the alkene, we're going to break the carbon-carbon pi bond. And what that's going to do is that's going to give us a new carbon-halogen sigma bond and put a radical on the carbon that was part of the alkene that is not bonded to our halogen. So our product is going to look like this. These are the valences that aren't being used. And then we have our radical here, okay? So this is very similar to protonation of an alkene. We would have protons add to alkenes and form carbocations. We can have radicals add to alkenes and form radicals. And similarly to how we form the more substituted carbocation by protonating the less substituted carbon of an alkene, we're going to form a bond between a radical and the less substituted carbon of an alkene to generate the more substituted radical. And a couple lectures from now, in our final lecture of the semester, we'll cover a reaction where just that takes place. Okay? So these two processes that I've shown you, very common processes that occur with radicals, you notice that they involve a radical reacting with a non-radical. And that's actually the most common thing that radicals do. They react with non-radicals. It's very rare for a radical to react with another radical species, and that's due to the fact that because radicals are high energy intermediates, their lifetime is short. They form, they react quickly, so you never have a very high concentration of radicals in a solution. So it's very unlikely for two radicals to collide with each other in a solution. Okay? It's unlikely, but it's not impossible. So it actually can happen. And we'll show you a couple examples. So if we formed halogen radicals, halogen atoms, we could have two of those halogens collide with each other. And this is how we would draw that process, showing the formation of a sigma bond between those two halogens. Okay? So rare, but not impossible. It is something that we do see from time to time. One that's more common involves oxygen. So oxygen has a couple of different forms, but believe it or not, the most common one is its diradical form, where we actually have two unpaired electrons in oxygen. And so because oxygen is fairly common, then oxygen can collide with a radical, such as a halogen atom. And you can form something looking like this. Okay? So oxygen colliding with another radical is the most common time that we see two radicals colliding with each other. And then we have compounds known as radical scavengers. This is something we'll talk about in more detail towards the end of the chapter in our final lecture on chapter 15. But a radical scavenger is a compound that will react with a radical intermediate to form a more stabilized and less reactive radical. Okay? And that's going to be very valuable because radical processes damage our DNA. Radical processes damage our fatty acids. Radical processes damage oils, unsaturated fatty acids, and consumer products. And it would be in our best interest to be able to inhibit those undesired radical processes. And that's what radical scavengers will do. That's something we'll talk about in that final lecture. Okay? So for the remainder of this lecture, we're going to talk about or introduce the reaction known as alkane halogenation. So alkanes are unreactive species, we learned back in chapter 4, but they do have some reactivity. They're not completely inert molecules. So we can take an alkane, and we'll just represent it like this because it's only one of the hydrogens on the alkane that we're interested in that's going to react. We can react that with a halogen in the presence of heat or light, and we can have a substitution process take place where we replace one of the hydrogens on our alkane with a halide, and then we're going to generate HX as a byproduct. So as you can see, this is a substitution reaction, but it's clearly not an SN2 or an SN1 reaction because we're using hydrogen as a leaving group. We would never use hydride or H- as a leaving group in an SN2 or an SN1 reaction. That's just not going to happen. But in a radical reaction, we can replace a hydrogen atom with a halogen. This process only works with chlorine and bromine. fluorine is too reactive. This is something we've talked about before. It's a very violent process. You're not going to want to heat up fluorine. And then iodine is too slow. So we're not going to see these reactions with iodine. Okay? So a couple examples. So we could take cyclohexane. We could react cyclohexane with bromine. We can heat up the reaction mixture. We've got to heat it up pretty hot, usually pretty close to 200 degrees Celsius. And we would generate bromocyclohexane. And then we would form HBr. If we chlorinate methane, we'll generate chloromethane. And of course, we'll form HCl in the process. But we can also chlorinate the product. Okay, we could react, the chloromethane could also react with chlorine in the presence of light. That's going to give us dichloromethane and another equivalent of HCl. And the dichloromethane could react further to generate chloroform, which could react further to generate carbon tetrachloride. Okay, so we have a problem with halogenation, and that is controlling it and getting it to stop at a monohalogenation, because these products are reactive, similarly of comparable reactivity to the starting alkanes. So the way we control this process, the way we ensure that we only obtain the monohalogenated product, is we use the alkane in excess. If we have an excess amount of the alkane, then the concentration of the alkane is always higher than the concentration of the alkyl halide product. So that's how we suppress polyhalogenation, by using an excess of the alkane. So unless you are told differently, you can assume that in any halogenations any halogenation problems you encounter, that excess alkane is being used, and that we would only be obtaining monohalogenated products. Okay, so you don't have to worry about polyhalogenation unless it is specified that that is the case. Okay, but even if you're only having monohalogenation, there is more than one possible product if there is more than one type of hydrogen atom in your alkane. So here we have propane. We can react propane with chlorine. We have two different types of hydrogens in propane. And so we have two different products that can form. As we will learn in our next lecture, both of those do form. So a common type of problem you'll encounter is one that asks you how many different monohalogenated products or monochlorinated products could be formed from a given starting material. And that's essentially asking you how many different types of hydrogens there are in that compound. Okay, so that will conclude today's lecture. And then we will continue with a more in-depth discussion of the halogenation reactions.